So, my dear friends, in today's class, we are going for the revision of the sum of the problems. That is the subject of EDC, electronic device and circuits, where we are going to solve the various level problems. Okay, and in the year 2004-25 batch, I have completed all the concepts of the EDC is concerned, my dear friends. Okay, so what are the things I am going to tell you? Very, very important itself is that see, today's session is completely regarding the problem solving, because in EDC I have been covered the semiconductor devices. Second one is very, very important is that, my dear friends, is that PN junction theory. Third one itself is that very, very important is BJT. Fourth one is very, very important itself is that very, very important is a MOSFET. Okay, but generally maximum problems in the EDC will be covered from the semiconductor theory and the PN junction theory as well as the syllabus criteria. The syllabus criteria, okay, of the GATE 2025 is concerned, my dear friends. Okay, so ultimately what I'm going to tell you itself is that say today I'm going to solve some of the important problems, and wherever the problem comes into picture, there I'm going to tell you if there is any particular theory that are related to that particular concept. I am going to explain, my dear friends, in a very detailed manner, my dear friends. Okay, so ultimately, so can I proceed the session, my dear friends, over here? Okay, can I proceed the session? Okay, my dear friends. So I told you pretty important itself is that see, we are covering the exercise 1 in the today's class, and tomorrow we are going for the some more numericals over here. Okay, so the subject name itself is the electronic devices and circuits, my dear friends, which is pretty important over here. At the same time, in this one, I am going to cover the theory of the semiconductor theory, or semiconductor diodes, or simply we are going to call it as a theory of semiconductors over here. Okay, now my dear friends, pretty important itself is that I am going to solve the various important questions, my dear friends, over here. Okay, the first question that has been asked, my dear friends, in in 2004 itself, which is pretty important, my dear friends, is that see, the impurity constant, that is what I'm going to tell you, that the impurity commonly used for realizing the base region of a silicon NPN transistor. Okay, base region of a NPN transistor, my dear friends. Okay, generally, I'm going to tell you itself is that very important, my dear friends, is that say, if I'm going to use the N-type semiconductor or P-type semiconductor in N-type semiconductor, or if I'm going for the P-type semiconductor, very important itself is that I told you the two shortcuts over here. Okay, so in N-type semiconductor, I'm going to use the pentavalent impurities and shortcut name is POB. Okay, I'm going to call it as a POB. Okay, POB means phosphorus, arsenic, antimony, bismuth. Okay, phosphorus, arsenic, antimony, bismuth. Okay, so when it comes into the P type, I am going to use the trivalent impurities like this is POP. POP is a shortcut that generally Amitabh Bachchan. Okay, Amitabh Bachchan, Amitabh, PA movie, and Amitabh Bachchan. Like that, we kept a shortcut. Okay, here ultimately I am going to say itself is phosphorus, arsenic, antimony, and bismuth. Okay, and P I am going to call it as a P-type semiconductor. I am going to use the trivalent impurities like Bagi. I am going to use the trivalent impurities like Bagi, my dear friends. Okay, this is what the question number 1 over here. Okay, so boron, aluminium, gallium, indium. Boron, aluminium, gallium, and indium. That is the trivalent impurities. Okay. Now here, what I am going to tell you is pretty important, my dear friends, is that now I am taking a NPN transistor. Okay. If I am taking a NPN transistor, pretty important here is that see here, NPN transistor is very important here. See, if I'm going to take it, this is NPN N. This one is what, my dear students? Emitter. This one is base, and this one is collector. This one is a collector. Okay. Now, my dear students, he is asking the base region. The base region is this P-type semiconductor. Okay. So the common impurity, what kind of that is P-type? What kind of impurity I have chosen for P-type? Okay. I told you that is for P-type, either I have to use boron, aluminum, gallium, or indium. So here, what is this here? Very, very important itself is that say that is used for realizing the base region of a silicon. Base region of a silicon, my dear friends, which is very, very important, my dear friends. Okay. Anyhow, we are going to use all these things over here. So here, very, very important itself is that say this is the fifth group, not at all preferred. Fifth group, so it is pentavalent, it is not at all preferred. But boron, aluminum, and gallium, all are third group only. All are third group elements only. Okay. These are all third group elements. Okay. So in these third group elements, I am going to prefer generally boron. Boron. I am going to prefer the first element itself is the boron, my dear friends. Okay. Which is pretty important over here. Order-wise priority. So the boron itself is the best suitable material, my dear friends. That will be here doped for the base. So option itself is what, my dear friends? Option C. Option C is the here the thing I would like to bring it to your notice, my dear friends, over here. Okay. Similarly, I am going for the next question. Okay. What is the second question? See here. Second question. Second question, my dear friends. Second question. Second question. Very, very important, my dear friends, over here. So, in this particular question, how the things are going to be taking place, my dear friends, those particular things also I'm going to explain over here. Okay. This is also asked in GATE 2004 paper, which is a very, very important question, my dear friends. So, what is the answer over here? He has given very, very important itself is that the resistivity, okay, the resistivity and see here, the resistivity of a uniformly doped n-type silicon sample, he has given the value, and electron mobility, he has given the mu n value is this one, and charge of the electron is this one. Now he is asking what is the donor impurity concentration in the sample. He is asking, my dear friends, this particular value over here. Now here I would like to bring, my dear friends, one thing. Okay, pretty important in your mind. I had shared all the theory, problem solving, okay, and formula oriented, all the notes in Telegram as far as EDC is concerned. All the problems, all formulas have been derived and everything is present, my dear friends, in my notes. So here I am not deriving the formulas. I am taking those particular formulas as a reference from my class, which I taught in EDC, and I'm going to use those particular formulas, my dear friends, over here, which is very, very important, my dear friends, over here. Okay. So he has given the resistivity. The resistivity always simply we are going to represent is pretty important. That is equal to indicated by rho, which is equal to if only given 0.5 ohm centimeter. We only given, and my dear friends, if I need to find out the conductivity, why I am finding out the conductivity, later I am going to tell you. The conductivity is indicated by this is the conductivity. Okay, it is conductivity. It is indicated by 1 by rho, that is equal to resistivity, my dear friends. Okay, then if I am doing over here 1 by, very important itself is that what are the parameter I am going to take it. Those particular things are pretty important, my dear friends, over here. So those things I am going to take it one by one over here. Okay, now see, I need to find out the certain formulas over here. So you're getting, if I'm going to take it as 0.5 and this one is equal to ohm centimeter inverse. First of all, let me find out the conductivity. then you are getting this value is equal to 2 ohm centimeters. And my dear friends, he has given the, all things are given in centimeters only. So mu n, which is equal to 1250 centimeter square volt second. Centimeter square volt second. He only given the mobility. Okay, the electron mobility. N means the electron mobility, my dear friends. Okay, and he has given the charge of the electron. This charge of the electron is indicated by the simple letter. What are the letter, my dear friends? I am going to take it here itself is indicated by Q. I am indicating by Q, my dear friends. Okay, so here completely, if I am going to take it, what type of sample it is? N-type silicon sample. Okay, if I am going to take it N-type silicon sample, what is the formula? So for this, N-type silicon sample, if I have taken, my dear friends, very important itself is that I told you the formula for the conductivity. The conductivity in N-type, which is equal to, very important is Q into mu N into small n. Small n, my dear friends. Okay. But in N-type semiconductor, N is equal to Nd. P equal in P-type semiconductor. Okay, in P-type semiconductor, P equal to Na. So, in N-type, it is nothing but D stands for donor, N stands for concentration. N stands for concentration, my dear friends, which is equal to very important, my dear friends. Okay, I am representing again this particular formula in the next. Okay, I am writing, my dear friends, this particular formula over here, which is pretty important, my dear friends, is that so then what happens, the conductivity in N-type, which is equal to Q, okay, into mu N. In place of N, I am writing Nd. Now he is asking the Nd value. Nd is equal to rho N, that is equal to conductivity N-type divided by Q into mu N. So here if I am taking the conductivity, so that is equal to 2 by, and again the charge of the electron, you only given 1.6 into 10 power minus 19. My dear friends, he has given the value. See here, the value of what, my dear friends? Here, mu n value in centimeters square per divided by volt second. Okay, which is equal to 1250. All things are in centimeters only, numerator and denominator. So you are getting, so here I am getting, my dear friends, this is Nd. This is Nd. Therefore, Nd is equal to, divided is whatever the value I am going to get, my dear friends, is equal to 1 into 10 power 16. You can use your calculus while doing the problems, my dear friends. Okay, per meter cube. Per meter cube. So what is the option here? So is there an option? Say here, all are. It is the option itself is that equal to, all are in centimeter, sorry, centimeter cube. So option itself is what, my dear friends? B. The option is B, my dear friends. Okay, like that, we need to solve the problems, my dear friends, which is equal to very important, my dear friends, over here. Okay, similarly, I am going to solve the next problem over here. Okay, that is problem number 3. Problem number 3. Choose the right response from the question given below. The band gap of the silicon at room temperature. The band gap of the silicon at room temperature. Generally, my dear friends, already I told you these particular values in your direct values. Okay, you need to, at the gate level, you need to remember those particular values. Okay, anyhow, my dear friends, see at room temperature. At room temperature means at 300 degrees Kelvin, because room temperature is nothing but what, my dear friends, see, that is equal to 27 degrees centigrade. Okay, room temperature is nothing but at generally at T equal to 27 degrees centigrade. Okay, so here what ultimately I'm going to do is pretty important. My dear friends, is the band gap is indicated by G at room temperature is T, my dear friends, which is equal to, that is equal to this particular value, my dear friends, the energy gap EGY, I'm going to tell you, my dear, minus beta into T. Now, if I'm converting these 27 degrees into Kelvin, then add, how we are getting 27 plus 273 degree Kelvin. You are getting this value is 300 degree Kelvin. You are getting these particular values, how much, my dear friends? 300 degree Kelvin. So, what is EGO? The energy gap at 0 degree Kelvin. So, this value is, my dear friends, is always, it is constant, and this value is equal to 1.21. Okay. And my dear friends, the beta value is a constant value, and this value for silicon and germanium are different, because for beta for silicon, this is a value, because generally he is asking for silicon. Okay, silicon itself is that 3.6 into 10 power minus 4 into 10 power minus 4, and a beta for germanium, this value is equal to 2.23 into 10 power minus 4. This is what, my dear friends, the value for the germanium over here. Okay. Now, but he is asking for silicon. He is asking for the silicon, my dear friends. My dear friends, now substitute the energy gap at room temperature is 300 degree Kelvin. This is what, my dear friends, 300 degree Kelvin. So, if I am going to use this particular value, 300 degree Kelvin over here, then the value it shall be equal to beta value, substitute 1.21 minus silicon, it is equal to, so the beta value as usual, that is equal to 3.6 into 10 power minus 4, and temperature 300 degree Kelvin. So after doing this particular value, my dear friends, which is equal to pretty important, you are getting the value is equal to 1.102 electron volts. You are getting, my dear friends, the value itself is equal to 1.102. Approximately the answer itself is that near 1.102 near value C. This particular value, my dear friends, we are going to use over here, which is very important, my dear friends, over here. Next question, because like this, the questions will be there, my dear friends, over here. Similarly, I am going for the next question. Question number 4. Question number 4. The primary reason for the widespread use of silicon in semiconductor, it's a very important question. Generally, in today's generation, what happens, my dear friends, is that we are completely in chip side. We are designing the various products, semiconductor devices. There, the raw material for the substrate, we are going to use silicon only. We are going to use what, my dear friends, is that silicon only, my dear friends. Okay. So for that, the thing itself is that very important, my dear friends, is that how I am going to use this particular thing, my dear friends, is that, let me go for the answer, my dear friends. Okay. See here, what is the reason for the silicon I am going to prefer? The abundance of the silicon on the surface of earth, it is right only. But main reason, large band gap of silicon in comparison to the germanium, because all are important. Favorable properties of silicon dioxide, lower melting point. Whatever it may be, my dear friends, all these things are the reasons for preferring the silicon. But I want to have the main reason. I want to have the main reason, my dear friends, which is equal to very important over here. Okay. And very important itself is that, and what is that particular value also we need to know, my dear friends. Okay. Here, I am going to use abundance of silicon on the surface of the earth. Okay, my dear friends, as a sand, because it is present on the surface of the earth as a sand. The next, very important, favorable property of silicon dioxide. SiO2 can be used as a best insulator. We are going to use as a best this one as a insulator. So, my dear friends, is that SiO2 can give best electrical characteristics. SiO2 can be used as an insulator. It forms as a layer in the fabrication of the MOSFET. That is another point. But thing itself is that, yet another point itself is that it can, so SiO2 can be a best electrical, having a best electrical, what is characteristics. Lower melting point. My dear friends, here, very, very important itself is that, my dear friends, is equal to, say, here, lower melting point, I am going to tell you, but maybe the thing itself is that SiO2 or silicon, sorry, a silicon, I am going to prefer. Why means the silicon support higher temperature. It supports at the higher temperature compared to the germanium. So when it comes into this one, this thing I won't agree. This thing I won't agree because lower melting point is nowhere agreeable, my dear friends, when compared to germanium. Okay, it is wrong. Why means silicon supports the higher temperature. That is yet another option. So out of these three options, the best primary reason is that the B. Why it is B? I am going to tell you, my dear friends. Why the option B? Why the option B is that, my dear friends, is that very, very important is that the band gap. The band gap, my dear friends, which is pretty, pretty important. The band gap of silicon, how much it is? The band gap is indicated by simply the energy gap. The energy gap of the silicon, very, very important, is that 1.21 electron volts. But the energy gap of germanium, that is equal to Eg, which is equal to 0.782 electron volts. So because of the large band gap of silicon, we are preferring the silicon, okay, over germanium. So out of these reasons, the best apt answer is the option B, my dear friends. The best option is what, my dear friends? Option B. That is very, very important point. Just I would like to bring it to your notice over here. Next question. Next question. Question number 5. Say the first study the question number 5, my dear friends. Question number 5. This question is asked in GATE, okay, which is pretty, pretty important, my dear friends, is that GATE 2004. So, very, very important. What is the answer for this particular question, my dear friends, which I am going to tell you over here. Now, here, the silicon sample A is doped with 10 power 18 atoms per centimeter cube of boron. Another sample B of identical dimensions is doped with 10 power 18 per centimeter cube of phosphorus. The ratio of electron to hole mobility is 3. The ratio of conductivity. Now we need to bring back the terms, my dear friends. Very, very important itself is that bring back the relation. Bring back the relationship, with my dear friends, in between the ratios in between conductivity and mobility. In between the conductivity and mobility, my dear friends. Okay. Silicon sample A is doped with boron. Sample A is doped with boron. Okay. With how many atoms? This number of atoms. So sample A is doped. Boron itself is a trivalent impurity. When it is doped with sample A, it forms like, my dear friends, so sample A is doped with 10 power 18 atoms per centimeter cube of boron. Then it forms like a what, my dear friends? I am doping with boron, my dear friends. Then it forms like a p-type semiconductor. Then what happens? Then Na is equal to 10 power 18 atoms per centimeter cube. Next question. Sample B is doped with, listen here, 10 power 18 atoms, same centimeter cube of phosphorus, this time P, phosphorus. Then when it is doped with that thing, my dear students, it forms like a N-type semiconductor with a donor concentration Nd equal to 10 power 18 atoms per centimeter cube. Already we have derived the various formulas. And that very, very important itself is that he has given one more clue. The ratio of electron to hole mobility, not the ratio of electron to hole mobility. So very, very important, my dear students, electron to hole mobility is 3. Okay. Then the ratio of conductivity he is asking, my dear students. Okay. The ratio of electron to hole mobility. So here I am taking, my dear students, mu n by mu p, which is equal to 3. My dear friends, so here we need to study the questions in a greater formats. Okay. In the greater formats only, we need to study the question, my dear friends, which is equal to very, very important, my dear friends. Okay. Okay. So this time he has given it is 3, not 1 by 3. Now he is asking the ratio of conductivity of sample A to B. He is asking the conductivity of sample A to B. Now he is asking, my dear students, he has given 3 over here. Now he is asking the conductivity of the sample, which is pretty important, of A to B. So he is asking what is the value of this y, this, my dear students. He is asking what is the value of this thing. Okay, which is pretty important, my dear friends. Okay, so generally, if I would like to take one important thing, the formula, the remembrance formula, my dear friends, is that see here, the question we need to study. First, we need to study the question completely. Then we are going to solve the things, my dear friends, which is pretty important, my dear friends. Okay, so the ratio of what he has given, my dear friends, see here. Conductivity of sample A to B. So conductivity of sample A to B. The conductivity formula I told you, my dear friends. A means, see, very important itself is equal to Q into A means it is a P-type semiconductor. Okay. P into Na divided by Q into it is B, which is equal to mu N into Nd. Okay. Nd, my dear friends. Okay. Very important is that this thing, my dear friends. Okay. Now, very important thing itself is that, my dear friends, whatever it may be, the doping concentrations are same. So Na equal to Nd, both are same. So here, which is equal to, cancel this thing, which is equal to mu p by mu n. But my dear friends, he has given mu n by mu p. Mu n by mu p, he has given itself is equal to 3. He has given itself is equal to 3. So mu p by mu n becomes, what happens, my dear friends? 1 by 3. So here the answer itself is equal to, so the ratio of A to B, conductivity, is equal to what, my dear friends? Option B. Option B, my dear friends. Okay. So if it has given 1 by 3, then you are getting it is 3. But he has given itself is 3, then you are going to get, my dear friends, is equal to 1 by 3, my dear friends. Okay. Another important formula. Just I would like to bring it to your notice, my dear friends, over here. Okay. Is that clear up to here, my dear friends? Okay. Similarly. Next question. Question number 6. Sixth question, my dear friends, which is pretty important, my dear friends, itself is that how the things are going to be varying, my dear friends, that we need to see over here. Okay. So very, very important itself is that, say, we are going to see the first, the sense the question, understand the question. That is very, very important, my dear friends, over here. Okay. Here also, the question is that the concentration of minority carriers in an extrinsic semiconductor under equilibrium A directly proportional to the doping concentration C. Inversely proportional to the doping concentration, directly proportional to the intrinsic concentration, inversely proportional to the intrinsic concentration. So these are the 4 parameters, my dear friends. I would like to bring it to your notice over here. Okay. Now, what is the answer in these particular 4 things, my dear friends, that we need to say over here? Okay. The question will be like this only. Okay. So we need to check the question properly. Then we need to go for the answer, my dear friends. Okay. So minority carriers in an extrinsic semiconductor. So if I'm going for the minority carriers, my dear friends, is that doping concentrations, and he has given intrinsic concentration. By seeing this particular question, you came to one notice that we need to use the mass action law. What does the mass action law says? Mass action law says mass action law says N into P, which is equal to Ni square. Okay, what is Ni? Ni is the intrinsic concentration. Okay, my dear friends, which is pretty important, my dear friends. Okay, the concentration of minority carriers in an extrinsic. Minority carriers. Generally, we are preferring N-type or P-type semiconductor. Generally, we are going to prefer always a N-type semiconductor because the mobility of electrons is more when compared to the mobility of holes. Always mu n is greater than mu p. Here, he is asking the minority carriers. So, minority carriers, my dear friends, let me go for it. Very important itself is that, my dear friends, is that we need to check over here. So, here, because I told you generally we are going to prefer the N-type semiconductor. For N-type semiconductor, N is equal to Nd. So, here, Nd into P, which is equal to Ni square. Okay. Now, minority carriers means this is nothing but P. This is nothing but P. P is equal to Ni square divided by E and D. So, what, my dear friends, here, what is happening, my dear friends? Very important itself is that, see, the minority carriers is directly proportional to the square of the intrinsic concentration is there? No, square is not there. And inversely proportional to the doping concentration, it is there. This is inversely proportional doping concentration. So option is what, my dear friends? Option itself is B. The option itself is B, my dear friends. Next. Question number 7. So here also, my dear friends, we need to check every time. Very important itself is that, see how the questions will be there and how you are going to get the reply. Those things are also very important, my dear friends. Okay. See, under low-level injection assumption, the injected minority carrier current for an extrinsic semiconductor is essentially, my dear friends, which is pretty important over here. Okay. So, he is asking, my dear friends, is that under low-level injection assumption, the injected minority carrier current for an extrinsic semiconductor is essentially what, my dear friends? Is essentially what, my dear friends? Very important, my dear friends, over here. Okay. So, if I would like to tell you about these things in a detailed manner. Generally, two equations are there. One equation is the, because extrinsic semiconductor consists of two types of currents, generally drift current and diffusion current. Drift current and diffusion current, my dear friends, okay, which is a pretty important thing. Just I would like to bring it to your notice. Okay, so I would like to bring first write down the term for, because extrinsic semiconductor, generally we are going to prefer the n-type semiconductor only generally. So this is also with respect to the minority carrier current. So Jn is a current density. The term itself is equal to Nx mu n into x q into E x. This is the formula. Already, my dear friends, I told you all these formulas are here in your general notes, okay, which is equal to n of x, mu n of x, and q into E of x plus that plus it consists of another term itself is that q into dn into dn of x by dx. What is this term? This term is called drift term. And this term is called, what is this term? Diffusion term. Is called a diffusion term. So he is asking the minority carrier current. The minority carrier current, my dear friends, is that very important itself is that the minority carriers means generally the injection, low level injection. So low level injection means very important is very less. So my dear friends is that so here what happens here I am going to take it the injected minority carrier means the under low level injection means what happens, my dear friends, is that the n of x is very less. And it is very less, my dear friends. So the drift term we can ignore. We can ignore because it is very less. Very less means at one time it is what happens, my dear friends, it becomes zero. So only it contains what, my dear friends, here. It consists of the two currents. One is the drift term and second one is the diffusion term. But all the things he has given, my dear friends, in the form of diffusion, drift recombination, and all those things, my dear friends. So what is the term that is left? Diffusion. So here, the injected minority current for an extrinsic semiconductor is because of the diffusion. Because of the diffusion. Diffusion is nothing but, my dear friends, the rate, the concentration of the charge carriers from the high concentration region to the low concentration region. Okay, this is what, my dear friends, over here. So ultimately, what is the term that is left over here? The term that is left here itself is what, my dear friends? The term is the diffusion term. So here, because it is ignored, so the under low level, this particular current I am going to call it as a diffusion current. Okay. So here itself is what, my dear students, is that so option is A. Option itself is what, my dear students, A. That is what, my dear students, we are going to get the formula here. Next, question number 8. The majority carriers in a n-type semiconductor have average drift. Average drift, my dear friends, which is very important, my dear friends, itself is that average drift, say drift velocity v in a direction perpendicular to the uniform magnetic field B. The electric field E is induced due to the Hall effect, acts in the direction. So he has given the four options B cross B, B cross V, along V, opposite to V, my dear friends, which is this one. Okay, generally, I would like to tell you one important thing over here. We have already studied Hall effect. We have studied, my dear friends, the concept of Hall effect, my dear friends, which is pretty important, my dear friends. So here, very important itself is that if I am going to see about the Hall effect diagram. So here, ultimately, the parameters that I would like to take it in your account itself is pretty important, my dear friends, is that say I am going to take it the three axis here. This is axis. This is one axis. Okay, like that. It is having the three important axes, my dear friends, X, Y, and Z. Suppose I am going to call this is X. Okay, this is Y. If I am going to call this axis is Z. Is Z, my dear friends. Very important. So here the uniform magnetic field in the direction, this is according to the Hall effect. I'm going to take it as a semiconductor, n-type semiconductor. So B, and this B is in direction perpendicular to V, perpendicular to the V. Okay, now he is asking what is the electric field induced due to the Hall effect. The electric field that is induced, my dear friends, in the Hall effect. Okay, so that particular thing, my dear friends, I would like to tell you. Generally, Hall effect always obeys what kind of formula? Hall effect always obeys the Lorentz force formula. Okay, so what kind of formula? Lorentz force formula. Lorentz force formula. So what does the Lorentz force says that, my dear friends? The formula is pretty important, my dear friends, is that we need to take it F is equal to Q, my dear friends, which is equal to, we are taking the vectors in all the general directions over here. So the Q into vector B into V. This is the formula. Already I told you, my dear friends, in your class notes. Okay. So what happens? The electric field, that is because F is equal to, what is the formula? F is equal to Q into E. So here E value is equal to B cross V. So option is what, my dear friends? B. Option itself is B, my dear friends. This is next question. Question number 9. See, now how the things are going to be happen, my dear friends, in the question number 9. Just we need to see over here. Okay. See, every time he has given the parameters, my dear friends. Don't get confused, which is pretty important over here. Okay. And first of all, we need to sense the question, which is pretty important, my dear friends. Okay. So the thing itself is that first understand the question. Okay. Very important. A heavily doped n-type semiconductor has a following data. Hole to electron mobility is 0.4. Doping concentration, he only given is this value. intrinsic concentration, E only given is this value. The ratio of conductance of n-type semiconductor to that of, okay, to that of intrinsic semiconductor of the same material at same temperature. Conductance of n-type semiconductor to that of intrinsic semiconductor of same material and at the same temperature is given by GATE 2006 question. This is what, my dear students, is that GATE 2006 question, my dear students, which has been asked over here. Okay. Now, how to do this particular problem? Okay. Now, you can do the problem, my dear students, for your end. I am going to tell you from my end. See here. He has given in the data. Take all the parameters one by one parameter, my dear friends. He has given very, very important mu p by mu n. This is volt electron mobility. .4 he only given, and doping concentration n type because it is n type. So in ND is there. ND, n type semiconductor. Okay, very, very important. ND. Per meter cube, my dear friends. Now he is asking the conductivity of n type and to that of the intrinsic. Now conductivity of n type and conductivity of intrinsic to that of intrinsic, my dear friends. The formula, please go for the previous notes, my dear friends. There you are going to get this one, which is equal to Q into mu n into ND divided by Q into Ni into, very, very important, mu n plus mu p. Go for the, because I am not deriving the formulas over here. Already this formula I told you, my dear friends, very, very important over here. So here, ultimately, if I am taking here the mu n is there, take in the denominator mu n as common. This formula already we got it, my dear friends. Already this formula we got it for the intrinsic concentration. We have derived in our notes. Go for it. So mu n will be taken common here, Q into ND divided by Q into Ni into, take it mu n common. If I am taking mu n common here, then it will be 1 plus mu p by mu n in the denominator. So here, this thing and this thing will get cancelled out. Q gets cancelled out, my dear friends, which is equal to, very, very important here. So here, ND is there in the top, and here 1 plus Ni, keep it Ni common here. He has given the very, very important, my dear friends, doping and intrinsic also he has given. This is intrinsic concentration Ni. Okay, in the denominator it is equal to 1 plus mu p by mu n. This is what here? This is in the denominator. Now, my dear students, I am writing in the next page the ratio of conductivity in n type divided by conductivity in intrinsic concentration, which is equal to, now only I have written the formula, which is equal to Nd divided by Ni. Now substitute the values. Nd is equal to Nd value. See here already it is there. And mu p by mu n value is there here. Intrinsic value, substitute all these values. Then it will be one plus, very, very important is that mu p by mu n. Then you are getting this value is approximately how much is 20,000. So option D. The option itself is D, my dear students. Okay, this is about the 9th question. Okay, next 10th question. 10th question. Say here. Now, my dear students, in the 10th question, he is asking some other parameters here, which is pretty important, my dear students, is that say the electron and hole concentrations in an intrinsic semiconductor are Ni per centimeter cube at 300 degree Kelvin. Okay. If the acceptor impurities are introduced with a concentration of Na, the electron concentration per centimeter cube at 300 degree Kelvin. At 300 degree Kelvin, my dear friends, what is this particular value? Those particular things, my dear students, are pretty important here, over here. Okay. So, here the thing itself is that, say, we need to go for intrinsic semiconductor as given. First of all, let me go for the question itself is that intrinsic semiconductor means you have to go for the mass action law. Once again. Mass action law. N into P equal to Ni square. So very important, my dear students, is that say acceptor impurities are introduced Na, and my dear students, you are given that Na, the electron concentration is asking, my dear students, which is very important here. The electron concentration he is asking over here. The electron concentration, because here acceptor impurities are added means say intrinsic semiconductor added with acceptor impurities. Intrinsic semiconductor, when I am going to add ISC, acceptor impurities, then it forms like a P-type semiconductor. P-type semiconductor. It forms like what, my dear friends? P-type semiconductor. Okay. Now, my dear friends, in a P-type semiconductor, the electron concentration is asking. The electron in P-type semiconductor, because Intrinsic semiconductor is added with the acceptor. Acceptor is nothing but what, my dear friends? Trivalent impurities. Okay. So this formula will be changed here. N into P, P into P, which is equal to Ni square. Okay. But here P into PP in P-type semiconductor is equal to acceptor concentration. Now, he is asking the electron concentration in P-type semiconductor. So here, N into P, which is equal to Ni square divided by C. It is equal to Ni square divided by PP. What is PP? Here, N into P equal to Ni square divided by Na. Na, my dear friends. So what ultimately you are going to get, my dear friends, is equal to, what is the option here? This is N I square. This is, my dear friends, don't get confused here. This is somewhat typing mistake. This is what, my dear friends, is equal. This is Ni square divided by Na. This is. So option itself is D. What is the option, my dear friends? Is that the option itself is what, my dear friends? That is equal to D over here. Okay. Which is yet another important point. Just I would like to bring it to your notice over here. Okay. So, my dear friends, is that very, very important itself is that say I got these particular parameters over here. Okay. Now, if I would like to go for yet another important point is that the questions maximum are based upon the concepts and formulas only. Maximum, the questions are based upon the formulas and concepts only, my dear friends, which is pretty, pretty important point. Just I would like to bring it to your notice over here. Just I'm showing you the things that are pretty, pretty important, my dear friends, over here. Okay. Now, if I'm going for the very, very important here itself is that how I'm solving the one by one problem over here. Okay. Now, listen. Question number. Next question. Next question. Question number 11. In question number 11. Which of the following, my dear friends, is that which of the following is true over here? Which is pretty, pretty important, my dear friends, is that say a silicon wafer heavily doped with boron is a P plus substrate. A silicon wafer with light doped with boron is a P plus substrate. See here, very, very important itself is that, my dear friends, is that how you are getting the various options over here. Okay. This is also yet another important point. Generally, I would like to bring to the one thing to your mind itself is that lightly doped and heavily doped, normally doped. N and P are there. These are called normally doped. N and P, normally doped. Doping styles. N and normally doped. N type and P type is. Next is slightly doped. Is N minus P minus for N type and P type. Very slightly doped. Then it will be N minus minus P minus minus. Okay. Next one is, these are all the important parameters. Just I would like to bring it to your notice, my dear friends, over here. This is regarding the normally doped types and the important point itself is that regarding this one. Now I am going for the heavily doped. Heavily doped is N plus. Very heavily doped. N plus plus P plus plus. N plus and P plus. My dear friends, generally P substrate is forming, my dear friends, is P plus means nothing but heavily doped. Heavily doped is right. Now, when the P substrate is forming, when the intrinsic semiconductor is doped with trivalent impurities like boron, aluminum, bagi, gallium or indium, then it forms like a P type. So here itself is P plus means heavily doped. It is not a light one. So this is ruled out. See, heavily doped with arsenic. So here what my dear students, arsenic itself is a fifth group element, not a tri. This is ruled out. Again, lightly doped with arsenic. This is not here itself is a P plus, and moreover, this is heavily doped and this is arsenic is a fifth group. So option itself is A. Here with boron, it forming like a P. Heavily doped means P plus. Okay. So option is what, my dear friends? What is the option? A. The option is what, my dear friends, is that A over here. Okay. Like that, my dear friends, we need to solve the different questions over here, my dear friends. Okay. Next, I am going for the next one more important question over here. This is question number 12. Question number 12. Question number 12. Now, my dear friends, this time he is asking the question in a different format, my dear friends, which is equal to very, very important here. Silicon is doped with boron. Silicon is doped with boron to a concentration of 4 into 10 power. See here, silicon is doped with these atoms, and the intrinsic carrier concentration of the silicon is only given, and Kt by Q value is given. So the Fermi level of the doped silicon. So here, generally, my dear friends, is that very, very important is that, say, very, very important is that we need to see the Fermi level in these particular type of semiconductor. Here, boron, this is generally a P-type semiconductor. This is what, my dear friends, is that the P-type semiconductor. In this particular P-type semiconductor, what happens? Let me tell you. See, generally, if I am going to take the energy band diagram over here, energy band diagram over here. This is conduction band. This is VB means valence band, my dear friends. So this is conduction energy level EC. This is valence energy level EV. And my dear friends, is that very, very important is that always the Fermi level. The Fermi level lies exactly at the center. Okay. The Fermi level lies, the intrinsic Fermi level. This is intrinsic semiconductor lies exactly here in EFI. That is Fermi level lies, my dear friends, exactly at the center here. But in a p-type semiconductor, the Fermi level in intrinsic semiconductor is that the Fermi level lies at the center. But in p-type semiconductor, the Fermi level, my dear friends, is that here is near to the valence band. The Fermi level is near to the valence band. So if I am going to take it this particular gap, this gap is what, my dear friends, is that this is equal to EFI minus EFP. EFI minus EFP, my dear friends, which is very, very important, my dear friends, over here. Now, here the question is that, my dear friends, is that what is the question over here? Compare it to the undoped silicon, the Fermi level of the doped silicon. Now, my dear friends, here it is a p-type semiconductor. My dear friends, if doping increases, the Fermi level goes down. That is what is happened, my dear friends, over here, which is equal to very, very important, my dear friends, over here. So, here as doping increases, the Fermi level goes downwards. The Fermi level goes downwards, my dear friends. That's a, I'm writing that particular expression only, my dear friends. That is equal to using the parameters. What are the parameters that are present over here? See, EFI, EFP, and parameters like KT by Q. This is one particular parameter. And intrinsic concentration parameter. You got that intrinsic concentration parameter is equal to Ni. And here, what is this 4 into 10 power? This is equal to Na, using the parameters of Kt by Q, the parameters of Ni, the parameters of Na, using all these particular parameters. I am writing the expression here, which is equal to Kt ln Na divided by Ni. Na divided by Ni. This is the formula. Okay. Now, my dear friends, he is asking the this particular value over here. Okay. Already Kt, that is the formula. We know, my dear friends, very, very important itself is that equal to. So, already Kt by Q and all these particular values are there. So, utilize those particular value, my dear friends, here. So, what are the values you are getting? Substitute all these values. So, Kt by Q is equal to 25 millivolts into ln of acceptor concentration is Na, that is 4 into 10 power 17 atoms, see here, centimeter cube, divided by intrinsic concentration. Intrinsic concentration is equal to Ni, and that particular value is also pretty important, my dear friends, which is equal to 1.5 into 10 power 10 per centimeter. This is what here. Then you are getting this value is equal to 0.427 electron volts. But here, what I told you, as doping increases, the Fermi level goes down. So the Fermi level goes down. Goes down. See, now what is the option here? So Fermi level option itself is what, my dear students, is that C. Option is C, my dear students, over here, which is yet another important question. Just I would like to bring it to your notice, my dear students, over here. Okay. Next question. Question number 13. 12 is finished. Now question number 13. So in this particular question, the very important itself is that, see, in an N-type silicon crystal at room temperature, which of the following, okay, which of the following is the very important itself is the concentration of 4 into 10 power 19 per centimeter cube. Okay. Option A, silicon atoms. Option B, holes. Option C, dopant atoms. Option D, valence electrons. Okay. This is what, my dear friends, you are going to get the question, my dear friends, like this over here. Now, how to solve this particular thing, my dear friends, is very important over here. Okay. So, here, the thing itself is that in an N-type silicon sample, at room temperature, N-type, we only said that it is what type of semiconductor? N-type of semiconductor. Concentration, have a concentration of 4 into 10 power 19 per centimeter cube. My dear friends, he is asking. Okay. Now I told you, my dear friends, is that we need to bring back again the mass action law here. N into P, which is equal to Ni square, which is equal to Ni square, my dear friends. Now he is asking, which of the following has a concentration of 4 into 10 power 19 per centimeter cube? He is asking this thing. Okay. But we know that already the standard values have been uh, tell you in your general class notes. Okay. The intrinsic concentration values and all those things. Already I told you, my dear students, in your general notes. Okay. So here in n-type semiconductor, here what I am going to tell you itself is that, see, NP equal to Ni square, but this is leave it apart, my dear friends. And I told you in N-type semiconductor, N is equal to Nd. As usual, we know. As usual, we know, my dear friends. Therefore, P equal to Ni square by N. Then it is equal to Ni square divided by Nd, the donor concentration, my dear friends. Over here, he only given the donor concentration Nd value, which is equal to 4 into 10 power 19 per centimeter cube. You only given this Nd value. Okay. Ni square, Ni value, my dear friends, is that as usual value, the standard value everyone knows. This is for silicon sample, this value. Okay. That is equal to Ni equal to, very important is that 1.5 into 10 power 10 concentration. Okay. Ni square. This is the value, my dear students. You are going to get, my dear students, is that this particular value. Okay. So this is the value 10 power 10. Okay. Which is equal to, this is also per centimeter cube. Now Substitute P equal to Ni square 1.5 into 10 power 10 whole square divided by Nd value 4 into 10 power 19. Then you are getting this particular value is equal to 5.625 per centimeter cube. Per centimeter. This is a P value. 5.625 per centimeter cube. Okay. Already this value is equal to N, my dear friends. N value. Here N is equal to N is this value. This is okay. So my dear friends is that say the P value and N value here this is per centimeter cube and N value here this is more 4 into 10 power. This is only this one. So here N value is greater than P as per the condition. N value is greater than P. When N value is greater than P, then what happens, my dear friends, itself is that, say, N value, N equal to what, my dear friends, in ND, which is equal to donor concentration. So here, the option is C. The option itself is C, my dear friends. Okay. Very, very important. We need to take. And this is a standard value. Standard values already I told you, my dear friends, in your notes. Okay. So very, very important, my dear friends, itself is that over here. Okay. So the concentration he has given because it is a N-type at room temperature 27 degrees. So in N-type, N equal to where? ND. If it is a P-type semiconductor, I told you P equal to Na. Leave it apart. But I'm not taking that particular part, my dear friends. Okay. Since it is a N-type semiconductor. Like that, my dear friends, we need to solve the problem over here. This is question number what, my dear friends? The question itself is what? The question number, okay, that is 13. Next question. Question number 14. But here one important thing I would like to bring it to your notice every student is that when you are, okay, when at the time of gate examination, you can't derive each and every formula. Remembrance is very, very important. Whether it is EDC or analog circuits, whether it is communications, whatever it may be. You need to remember the formulas every time because at the gate writing the that is writing the gate examination is very, very important itself is that say at that particular point you don't have the time to derive each and everything. Okay. So what you have to do means you need to keep each and every formula on your papers. Every formula, what are the subjects you are going to learn on the paper first. Because there the time is very less. If you want to crack, my dear friends, the formula remembrance is very, very important. The formula remembrance is very, very important, my dear friends. Okay. Now, next question. The ratio of mobility to the diffusion coefficient in a semiconductor has a units of. What are the units, my dear friends, is asking over here. This is also very, very important, my dear friends, is that over here. Okay. See, generally, I told you the relation dn by mu n in n-type or dp by mu p, which is equal to Vt. And a dl means diffusion constant in n-type, mu n is the mobility in n-type, dp means the diffusion constant for, this is electrons, this is for holes, and mu p, mobility for holes, which is equal to Vt. Vt is equal to volt equivalent of temperature, which is equal to kT by q. But he has asked here reverse, because what is the Vt formula? Vt is equal to generally kT by q, which is equal to 25 millivolts. Whatever it may be, the units are volts. The Vt units are volts here. Now here, but the question is reverse here. Ratio of mobility to diffusion. He is asking mu by d. Mu by d means reverse. Then it becomes 1 by Vt. So what is the formula for Vt? Units volts. So mu by d units are is equal to V inverse. So what is the option, my dear friends? The option itself is what, my dear friends? Pretty important is A. Option itself is A, my dear friends, which is yet another important point. Just I would like to bring it to your notice. Okay. This is question number 14 over here. Okay. Next question. This is a linked answer question. This is very important, my dear friends, is that how the linking of the question we have done, my dear friends, over here. Okay. This question is very important, and this question will be again. Okay. See, sometimes the questions will be little bit of level 1, level 2 and level 3. Level 1 is 1 mark, level 2 is 2 marks, level 3 is linked answer questions, 5 marks questions, like that it is there. But your gate paper, when it comes into the criticality of asking questions will becomes high, but the questions will be of the, he is not mentioning level 1, level 2 like that. Okay, but whatever it may be, we need to study. This is the question that has been asked in the previous paper in GATE 2010. Okay, and this is one question and this is the second question, same question linked. Okay, which is very important, my dear friends. See here. First, listen the question or write the question. The silicon sample with a unit cross-sectional area as shown in below in a thermal equilibrium. The following information is given. Okay, now my dear friends, he has given very important itself is a silicon sample. Okay, he has given the very important itself is the silicon sample with a uniform cross-sectional area. See, he has given certain values, the charge of the electron, the Q value, okay, thermal voltage. Thermal voltage is also very important. Later I am going to do this particular thing later, my dear friends, over here. Okay, now here, and he has given the electron mobility. He has given this value is equal to mu n also. He has given, my dear friends. Okay, so now the question itself is that it is x is equal to 0 and x is equal to 1 micrometer. He has given Nd, means what type of silicon sample it is. Nd means this type of a, here this is a type of a N type. Nd means in N type semiconductor N equal to donor concentration. So I have taken this sample itself is what, my dear friends, is a what type of thing. This is a N type silicon sample. This one is a N type silicon sample. N-type silicon sample, my dear friends. So, very important itself is that, my dear friends, is equal to sample. He only tell that this silicon sample is in thermal equilibrium. He only mentioned here. The silicon sample is in thermal equilibrium. Very important point. When it is a thermal equilibrium, then what happens to the electric field? E equal to, generally we know the formula V equal to ED. V equal to ED here. But here, what are the distance? See here, the distance itself is very important, my dear friends, is equal to, see here, nothing D equal to what? Here, the distance I am taking with the parameter of L. So E is equal to V by L. E equal to V by L, my dear friends. Okay. Now see here. So the question itself is that the magnitude of electric field at x is equal to 0.5 micrometers. It is x equal to 0. This is x equal to 0. This is x equal to 1 micrometer. Now, my dear friends, he is asking, very important itself is that at which micrometer is asking. See here, 0.5 micrometers. 0.5 micrometers he is asking, my dear friends, which is very, very important here. So here E equal to V by D means V by L. So what is the voltage he has given? He has given the voltage is here 1 volt. So E is equal to 1 by L. Okay. And exactly he is asking, my dear friends, is that L value is 0.5 micrometers. Okay. 0.5 into 10 power minus 6. Okay. Then E is equal to, so you are getting, my dear friends, is that equal to, very, very important itself is that, see, the question I am going to do over here instead of here because the question answer is here. So E equal to electric field at X is equal to 0.5 micrometers. So it is 1 by, and the distance of half is asking minus 6 E equal to 10. Okay, because I am taking on the top by 5 into 10 power 6 minus 6. So here ultimately, or the question he has changed over here. Okay, the question itself is that he is asking, wait a minute here, he is asking at electric field at X is equal to 0.5 micrometers. Okay, which is see, my dear friends, here the question is at exactly at X equal to 0.5 micrometers. Okay, 0.5 micrometers is that, but he has taken completely at 1 micrometer. That is reverse. Okay, at 1 micrometer, it is different. Okay, okay, very, very important, my dear friends, is that so what ultimately you are getting is asking not at yes, here the question itself is a little bit wrong, my dear friends. The magnitude of electric field at 1 micrometer. That's what here. There is a change in the question. This is at 1 micrometer. At 1 micrometer, my dear friends. Okay. Then it will be E equal to, then it will be changed. That's what here. Because if he has, so V equal to, very, very important is that 1 volt. Okay. And the distance, you only given the distance here. This is 1 micrometer. This is at 0. Okay. So at 1 micrometer, he is asking, my dear friends, very, very important over here. Then it will be 1 by 1 into 10 power minus 6. Then E equal to, we can write down, my dear friends, this thing in the form of 10 power 6. E equal to, I will write down in terms of, my dear friends, see 10 cube into 10 cube. This 10 cube I am writing, my dear friends, is that, see here, E equal to 10. See, I am writing, my dear friends, here completely 10 cube. This I am writing, my dear friends, in 10 power 6 is can be written as 10 kilovolts per centimeter. You can change the same thing you are getting, my dear friends, over here because 10 power 4 centimeter is 10 power minus 2. I am writing this value like this. So option itself is what, my dear friends? The option itself is C over here. Okay. Sorry for that, my dear friends. A little bit of change over the question. Okay. Which is pretty important, my dear friends. Okay. So see, he has taken the silicon sample and he has done the all these particular parameters, my dear friends. Now I am going for the the linked answer question. Now, my dear friends, what kind of sample it is? It is completely a silicon sample. So, silicon sample. So, here very, very important itself is that the same sample is what type of sample? N type. So, here he is asking the magnitude of electron drift current density. Electron drift current density. Now, my dear friends, he is asking this time the magnitude of this particular current density, my dear friends, he is asking over here, which is very, very important, my dear friends, while doing this particular problem over here. Okay, this is also we need to check it and we need to do, my dear friends, which is very, very important here. Okay, so this is also at 1 micrometer, not exactly this one. This is one at 1 micrometer. Okay, change it to 1 micrometer. Now here, if I am doing, my dear friends, is that very, very important itself is that Z, because the magnitude of electron drift density is JD. JD, which is equal to ND mu N Q into E. Q into E. He only given the value of ND. See here, if I am going for all the values, see, I told you the value, electron density, see, electron mobility, this is mu N. Next, as he has given the ND value, yes, ND value here, see in the diagram, mobility, this is ND value, see here it is ND, ND is over here. Now substitute here, what are the values are every? ND equal to 10 power 16 into mu N, which is equal to 1350, all are in centimeter square only, into charge of the electron 1.6 into 10 power minus 19. Okay, ND is there. Here mu N I have taken, Q I have taken. Okay, and electric field, now only you got it. The electric field value you are getting, see here. This is value you are getting, my dear friends. All are have changed. This is 10 into 10 cube. All are in centimeters only. So it will be changed here, which is equal to, very, very important, my dear friends, is equal to 2 point. Okay. So again multiply here into 10 into 10 power 4, because that is equal to 2.16 into 10 power 4 into 10 power 4 ampere per centimeter square, because density is indicated by current by here, that is I by A, current by area. Current is amperes, area is in centimeter square. So you are getting, my dear friends, is that this is the answer. ND value, mu and Q and E values. First of all, in the linked answer question, first question is E value, electric field. Okay. So then option is what, my dear friends? A. Like that, my dear friends, we need to solve the question over here. This is a linked answer question. Okay, which is question number 15. A 15B. Next question. Question number 16. Question number 16 itself is a little bit of a simple question which has been asked, my dear friends, is that drift current in semiconductor depends on drift current the drift current in semiconductor depends on. This is a question, my dear friends, that is asked over here, which is very, very important, my dear friends, itself is that say how to get the answer for this particular question also, which is very, very important. It's a basic question. Okay. So very, very important itself is that like these questions, if they have been asked, my dear friends, is that say the drift current in a semiconductor depends on. Okay. So very important itself is that the drift in a it is a completely the drift in any particular semiconductor. Semiconductor consists of majority carriers and minority carriers. It consists of both majority and minority carriers over here. So if I am going for the same thing here, J drift. Okay, the drift current in any particular semiconductor consists of majority carriers and here the J drift, which is equal to Jn plus Jp. So here I have taken the J is the what, my dear students, is that the very important itself is the current density. In N type it is indicated by simply Q n into Q into mu n into E. Similarly, Jp is equal to P into Q into mu P into E. This is the formula. Generally, you are going to get, my dear friends. So, if I am writing here, the drift current in a semiconductor depends upon ultimately, see here, NQ mu n, take E outside, plus P Q into mu P into E. This is what, my dear friends, is that this is concentration and this is electric field. So the drift current depends upon the first one is this is carrier concentration and this is my dear students, because this is indicated by concentration. Yeah, N type concentration is indicated by N and P type concentration is indicated by P. These are nothing but the carrier concentration. Concentration. And this is what, my dear students, electric field. Electric field over here. So ultimately, what is the option, my dear friends? The option itself is C. The option itself is what, my dear friends, is that C, my dear friends. So this is about the question number 16 over here. Okay. Next, question number 17. Question number 17. You need to check and you need to get the answer, my dear friends, which is equal to very important here. See, when I'm going for the question number 17 over here, see here, a silicon bar is doped with donor impurities. Means silicon bar is doped with donor impurities means it is nothing but what type of semiconductor? N-type semiconductor. Intrinsic concentration at 300 degree Kelvin. Ni value is given. Assumably completely impurity concentration. The electron and hole concentrations. Now, my dear friends, is asking that assume complete impurity ionization. Okay, whatever it may be, my dear friends, there is no issue over here because we are going to get, my dear friends, here. See, impurity ionization means you are going to get, my dear friends, in the form of NO and PO instead of N and P semiconductors, okay, which is equal to very important, my dear friends, over here, okay. So here, very important, complete impurity concentration means impurity concentration, meaning mass action law is changed as mass action law will change like this. N into P equal to Ni square. When I am taking this particular term here, it will be NO, completely impurity ionization. PO equal to Ni square. But NO equal to ND. NO equal to ND, my dear friends, which is very important here. Then you are getting he is asking the electron and hole concentrations. Already, my dear friends, NO equal to ND. He only given this is equal to 2.25 into 10 power 15 atoms per centimeter cube. atoms per centimeter cube. Okay. And PO. If I'm taking the, my dear students, is that the PO, the value of PO is also pretty important, my dear students, is that what is this PO? Okay. This PO is that the whole concentration. Therefore, PO equal to Ni square by NO, impurity concentration in time, that is equal to Ni square by ND. Therefore, PO, which is equal to Ni square. My dear students, Ni values here always it is constant. This is constant, my dear students. Then it will be 1.5 into 10 power 10 whole square divided by ND value. Okay, which is equal to very important, my dear students, is that 2.25 into 10 power 15. Then it will be how much you are getting, my dear students. PO value equal to, you are getting this value is equal to 10 power 5, 1 into 10 power 5 per centimeter cube. This is what, my dear students, we are going to get over here. So ultimately, so the PO and NO values. So NO value he only given, my dear students. So we need to go for the PO value. NO value he only given, and PO value we got it now. So option is D. The option is what, my dear students? The option itself is D over here. Okay. Similarly, my dear students, next question. This is the question number 18 comes into picture. Now, my dear friends, in this particular question, he has asked a very important itself is that, see, electronic charge he has given. Okay. So, in that particular electronic charge, he is asking very important itself is that, say, the magnitude of the electron diffusion current density he is asking. Okay. He is asking very important itself is that, what is this one? This question is asked, my dear friends, very important itself in 2014 set number 2. See here, charge Q has given, KT by Q has given, mu N has given, concentration gradient of electrons in a p-type silicon sample, the magnitude of the diffusion current density, my dear friends, he is asking. Now, my dear friends, see, this is, he has given very important itself is that, electron diffusion current density. Electron diffusion current density, my dear friends, is that very important itself is that the formula. Okay. See, I told you we are going to get the formulas which are pretty important, my dear friends, is that how to solve these particular parameters. That is first point. See, and mobility has given, concentration gradient of electrons injected into p-type. So when it is injecting the electrons into p-type, what happens, my dear students, is not drift. Diffusion is happening. The diffusion is happening, my dear students. Okay. So he only given the Q value here and here. This is the injected into the p-type. So the injected into the p-type, which is nothing but what, my dear students? So 10 into 10 power, that is 10 power, that is this value over here. Okay. And this particular value is also very important here. How to get back those particular values also here. So when it is electrons are injected into the p-type, means this is nothing but dn by dx value. And electrons are injected into p-type, then it is equal to dn by dx, which is equal to 10 power 21 per centimeter cube. This is what here. Okay. Then, my dear students, he has given the charge as usual. You know, you have the value of this one. So here, the magnitude of electron diffusion current density, which is nothing but with respect to distance x. So here, Jn of x, which is equal to very, very important is that Q into VT into mu n into dn by dx. Okay, then it will be Q value is equal to 1.6 into 10 power minus 19 and VT formula. I already told you VT has given any value of VT. Yes, KT by Q is nothing but VT only. This is VT. Okay, which is equal to KT by Q is 25 millivolts is VT. VT equal to KT by Q, volt equivalent of temperature. So it is equal to 25 into 10 power minus 3 and mu n value here that is equal to 1000 centimeter square volt second into dn by dx, which is equal to 10 power 21. Okay, leave it apart these things. Later we can write down into 10 power 21. You are writing, my dear students, all this particular thing. Then you are getting this value equal to 4000. You are getting this value equal to 4000. So here, what are the options that are present, my dear friends, is that see, the options is not given over here. So here itself is that the current density. What are the current density you are going to get, my dear friends, is equal to here. That this is also what are the units here? You only given ampere per centimeter square. This is what here. Question number 18. Now question number 19. A thin P-type silicon sample is uniformly illuminated with a light. Okay. See, this is about the question, my dear friends. Sometimes the question parameters will be changed over here. Here, how the question will be very, very important itself is that saying how the things are changing here. A thin P-type silicon sample is uniformly illuminated with light, which generates excess carriers. The recombination rate is directly proportional to. The recombination rate is directly proportional to. Here I have taken. This is a P-type. Here I am projecting the light. When I am projecting the light on this P-type semiconductor, very, very important itself is that, see, here what happens when I am projecting the light, my dear friends, itself the recombination rate is directly proportional to, very, very important is that, see, here, what is the formula that is present, my dear friends, over here? Okay, so directly proportional to the, see, it is a P-type semiconductor. Holes are majority carriers. Holes means P-type in P-type. Electrons are minority carriers. Okay. The recombination rate is RR. Recombination rate is indicated by RR, which is equal to, very, very important itself is that recombination rate is equal to N by tau S. Tau S, my dear friends. Okay. Which is very, very important, my dear friends. Okay. Or you can take it, that is N by tau N. N is a minority carrier concentration divided by minority carrier lifetime. This is what, my dear friends. Here in P-type, what are the minority carriers? Electrons. Tau N is that minority carrier lifetime. So the this is what minority concentration. So very, very important itself is that what is the option? So excess minority carrier concentration. The recombination rate RR is directly proportional to this option. This is nothing but small n. Small n is the excess minority carrier concentration. Excess minority carrier concentration, my dear friends. Next, question number 20. This is also asked in 2000, my dear friends, itself is that, say, this particular question is also very, very important, my dear friends, is that, say, how the question will be there over here, okay? Now, he has given the whole mobility in a semiconductor mu p means it is nothing but p-type semiconductor, okay? And the whole diffusion constant is asking dp over here. He has given the t value and kt by q, my dear students, these particular values over here. Now he is asking this particular, my dear students, which is very, very important over here. I told you one important thing itself is equal to dn by mu n, which is equal to dp by mu p, which is equal to vt. Here, dp is equal to vt into mu p, okay? And dp is equal to vt value, you only given, this is nothing but vt, which is equal to 26 millivolts into mu p. Mu p is what, my dear friends, is that what is the value that is also he has given is 500 centimeters, this value over here. Now, what is the whole diffusion constant over here? Then you are getting this particular value itself is that how much, my dear friends, is that 13 centimeters square per second. This is what, my dear students, you are going to get the value like this, okay? So the whole diffusion constant is equal to this particular value over here, okay? Here also options are not given. Next, my dear students, I am going for the next question over here, okay? That is the question number how much? 20. Now I am going for the question number 21. So in the question number 21, how the things are going to be changed, my dear students, that particular thing also I am going to tell you, very, very important, my dear students, over here. Okay. So see here. Here I would like to bring one thing into importance over here. And those particular thing also I am going to depict you in a detailed manner. Okay. So what are the general things I would like to bring it to notice is that, see here. The question itself is that L this rho I is plotted as a function of 1 by t. This is plotted as a function of 1 by t, where rho I is the intrinsic resistivity. Rho I, this is what, my dear students, is the intrinsic resistivity, and t is the temperature. And a plot is almost linear. This is plot is almost linear, not completely linear. It is linear. The slope of this line can be used to estimate. For what purpose this line is going to be estimating, my dear students, which is very, very important, my dear students, over here. Okay. So, see, generally, I am going to take it resistivity versus temperature graph. Resistivity versus temperature graph, my dear students, which is equal to very, very important, my dear students. Okay. See, if resistivity is a parameter, generally, first of all, let me tell you one important thing, my dear students, over here, because that is pretty important itself, is that, see, I would like to bring one thing. The thing itself is that, see, I'm going to for the answer here. Later, I'm going to explain the concept over here. As see, as temperature increases, energy gap decreases. As temperature increases, my dear students, itself is that water energy band gap. Energy band gap decreases. Band gap of the, so the slope of the line is estimated. Finally, it is what the band gap energy of silicon. This is the answer. Leave it apart. But what kind of parameters we need to study, my dear friends, is that say very, very important itself is that say in intrinsic semiconductor, if I'm going to take it an intrinsic semiconductor, it consists of intrinsic semiconductor consists of both N and P, N-type and P-type concentrations. Okay. So here what happens, my dear friends, in intrinsic semiconductor, as the N and P increases, concentrations of N increases, P-type increases, then automatically what happens, my dear friends, the conductivity also increases. Conductivity increases. Okay. When the conductivity increases, because what is the resistivity? When conductivity is increasing means the resistivity decreases. The resistivity, what happens, my dear students, decreases. Okay. When the resistivity is decreasing, very, very important itself is that see the graph I'm going to tell you itself is that see it is rho. Rho versus rho, my dear friends. Okay. So here, what happens? The resistivity is, see, when the conductivity is increasing, the resistivity is decreases. Okay. When the resistivity decreases, my dear friends, very, very important itself is that, what is that? Okay. Resistivity decreases. Okay. So ultimately, here, one more important thing, I would like to bring it to your notice over here. Okay. So, when resistivity is decreases, then what happens? 1 by t, that is, as resistivity is decreasing here, 1 by t, what happens? 1 by t increases. 1 by t increases, my dear friends. Okay. Generally, what happens, my dear friends? When energy gap is more, here what happens? When the energy gap is more or energy increases, that is secondary. Here what happens? Here, if I am taking here, very, very important here, this is what the general thing itself is that. So ultimately, here what happens when conductivity increases, the resistivity decreases. Leave it apart over here. Okay. See, if temperature decreases, this is point, then the resistivity increases. When then what happens to 1 by resistivity? 1 by t. What happens with the 1 by t? 1 by t also increases. 1 by t, because here very, very important increases, my dear students. Then automatically what happens over here? L n of rho also increases. This is what over here we would like to get, my dear students, is that a very, very important point. Just I would like to bring it to your notice over here. Okay. This is the thing I would like to bring it to your notice, my dear students, over here. Okay. Next. So, like this, my dear friends, you are going to get the different formulas over here, which are very, very important, my dear friends. Okay, over here. Okay. Now, my dear friends, I am going for the very, very important here is that so ultimately, these are all the important things. Just I would like to bring it to your notice, my dear friends, in the today's class. Selvan, we are having the very, very important, my dear friends. Say the class which I am going to discuss in the next session is pretty, pretty important, my dear friends, is that say we are having some more important problems that I am going to discuss in the tomorrow's class. A beautiful session is going to be happening, my dear students, in the tomorrow's session on the EDC. Later, you have the enough time. You go ahead for your own preparation, my dear students. And thank you very much, Selvan, for attending the today's class, and Yoga Lakshmi and Harita. So, the students who are having the quite interest, please join over here. All these things are pretty, pretty important, my dear students, for the revision of the classes. Okay. Thank you very much, my dear friends. Anyhow, thank you for attending the classes. Thank you.